Go. Oh, hello, class. Well, you better be ready. Here we go. So today we're going to learn about the definite integral. Yeah, you've been finding antiderivatives or indefinite integrals, and those are functions. But we're going to find the definite integral over an interval, and it's going to give us a number. So we're getting back to numbers today, which is exciting. And it has to do with the area under a graph. So for the do now, I want you to find the area under the graph of y equals 2x. So give it a little sketch from x equals 1 to x equals 3. And that you can get the exact area under that graph from 1 to 3. Oh, here we go. Yeah, we're trying to find the area under the graph y equals 2x from x equals 1 to x equals 3. Gina. She got 6. Anyone else get 6? Anyone else get a different answer? Oh. There are actually people in this room, even though it's surprising. There are other people in the room. Just telling people at home so they know. Yeah. What shape is that? Trapezoid, right? So do you remember how to find the area of a trapezoid? Yes, you taught it to us. Of course we remember. 1/2. Uh-huh. Base. Oh. Well, how many bases does a trapezoid have? Nope. The bases on the parallel sides. Got 2 of them. What do we do with those bases? We add them. So it's 1/2 the sum of the bases times the height. Yeah. Okay. So what's the length of this base? What's f of 1? That's a 2. What's the length of the other base? F of 3 is 6, right? And what about the height, the distance from one base to another? 2. So the area under this graph equals 8. Now, it's impressive, I guess, but getting the area under a linear graph, if you can get the area of a trapezoid or a triangle or rectangle, you'll be fine. But what about finding the area under some curvy, crazy graph? Wouldn't that be cool if you could do that exactly? I'm here to tell you today, you're going to be able to find the area under any graph. Big day in your life. All right, and it all has to do with something called the Fundamental Theorem of Calculus. And I'm going to show you where it comes from. Basically, you just have to know how it works. But see if you can, like, bear with me for a couple seconds. I promise it won't be long. Don't worry. Suppose I have this curvy function here, which is y equals lowercase f of x. You see it? It's this thing here. That's just one function. Well, I can create another function. It's called an accumulation function. And the way I'm going to do it, I'm going to let capital F of x be a function that collects the area under the graph of lowercase f of x from a to x. So, like, for example, if I want f of a, that would be the area under this graph from a to a. Well, that's not going to give you any area, right? If you start here at a and you end at a, the amount of area would be 0. So f of a would be 0. F of b would be the total amount of area under this graph from a to b. I'm just making up a new function, capital F of x, right now. But what it does is it collects area under the other function, lowercase f of x, from a to whatever number you plug in. That's what it gives you. Okay. So suppose I just wanted the area of this piece here, which on my board is red. What I could do is I could collect the area from a to x plus h. That would be f of x plus h. And what would I have to subtract off from that just to get this one band here? Area from a to x, right? So if I wanted the area just of this piece here, I could take f of x plus h but that gives you too much area, and then subtract f of x. And that would give me the area of this band underneath this curve. Well, do you see that that would approximately be equal, that's almost equal to the area of this rectangle, where the width is h and the height is f of x. Let me go to my next page. So the area of one rectangle is, which would be f of x times h, is approximately, yes, if you can find that, equal to f of x plus h minus f of x. And it's really important when you're looking at this, understand that lowercase and uppercase are two different things. So that's how I'm getting this. Now, how am I going from this line to the next line? What am I doing? Dividing each side by h. Now, if this side equals that side, then the limit as h approaches 0 of this side equals, or is approximately equal to the limit as h approaches 0 of that side. Okay? So, but when we take the limit as h approaches 0 of this side, we get some crazy flashbacks, don't we, kids? Look at this in here. What? This reminds us of something. What is this? That's the definition of the derivative. So this left side, if we make h approach 0, these are now no longer going to be kind of the same. They're going to equal each other. And the derivative of this accumulation function, capital F prime of x, equals the limit of the other side. But the other side, there were no h's. So the limit of f of x as h approaches 0 is just f of x. So out of all this, we're saying the derivative of this accumulation function is just the function. If the derivative of cap f is the function, then the antiderivative of the function is the accumulation function. So when we're finding the antiderivatives of functions, we're actually finding this accumulation function. And this is a really neat thing. Let me just go here. If we take f of b minus f of a, remember f of b stood for the area underneath the graph of f from a to b? And capital F of a we said was 0, because that's the area under the graph from a to a. So f of b minus f of a is the area under the graph of f from a to b minus 0. So what it gives us is the area under the graph from a to b. If we take the antiderivative of a function and we plug in b and we plug in a and we subtract, we get the area under the graph of the original function. Now this is only true if the function is positive, and we'll talk about that, but it gives us a way to find the exact area under a graph. I know it's kind of a lot, you might want to look at it later or something, but it's neat. So with the conclusion of this, it relates a function to the antiderivative. It's saying the derivative of the antiderivative is the function, and the antiderivative of the function is the antiderivative. And this is known as the Fundamental Theorem of Calculus. Well, and just to show you how powerful this is the actual Fundamental Theorem of Calculus right here. What it's allowing us to do is save a whole bunch of time. Because if we wanted to get the area under a graph before, we'd use rectangles, right? But we'd be off. But if we made the number of rectangles approach infinity so that the width of each one approached 0, and then we added them all up, do you recognize the sigma? That means add them all up. So if we added up the width times the height for all these rectangles, but we made the width of each rectangle approach 0, we could get the actual area. But that would mean getting a limit. Now, with this, we're saying you don't have to get a limit to do this. You just evaluate what we call the definite integral. And the definite integral of a function is just the antiderivative of whatever the function is at b minus the antiderivative at a. And that's where the integral sign comes from. It comes from the sum of height times width. Each rectangle has a height of f of x and a width of dx, a small change in x. Very, very useful. So it's funny that halfway through the course, we finally get to the Fundamental Theorem of Calculus, Part 1. And that's all it's saying. It's telling us that we can, using the antiderivative, okay, we can evaluate a definite integral. We just get the antiderivative, plug in the upper limit b, a, and subtract. So I've listed these steps here. But understand that as long as the function is above the x-axis, it's positive. It gives you the exact area under a curve from A to B. You ready to practice? All right, so this is what we do. When you want to evaluate, if you see a definite integral, if you see an antiderivative, but you have these little numbers here, that's a definite integral. This number up here is called the upper limit of integration. Guess what they call the little number down here? The lower limit of integration. So you're going to actually get a number when you do this, which is exciting. We haven't seen numbers in a while. Okay, so we understand the process. You get the antiderivative of whatever the function is. You plug in the upper limit into the antiderivative. You plug in the lower limit of integration into the antiderivative, and then you just subtract. And that's your answer. All right, example time. Yours is not big like this. It says practice. Let's see if you can find this top of the page. We want to find the antiderivative of x squared plus 3. The definite integral of x squared plus 3 from 1 to 4. So what's the first thing? Let me just write that here. 1 to 4. X squared. I should have parentheses. Okay. So the first thing we have to do is get the antiderivative. What's the antiderivative of x squared plus 3? What was the first term? For the antiderivative of x squared? Okay, 1/3 x cubed plus 3x. And then it is plus c, but I'm going to show you why. I'll do it once, but we'll never need a plus c again when evaluating a definite integral. Because we get the antiderivative. Now when we get it, you put a line here, because you have to remind yourself you need to evaluate this from 1 to 4. Then what I like to do is I like to set up 2 sets of parentheses with a minus. Now, which number are we going to plug in first, the 1 or the 4? The 4. We have to plug in the upper limit first. So we've got our antiderivative. Everywhere we see an x, we're going to put in a 4. So 4 cubed, 64/3 plus 3 times 4 is 12. And I'm doing the plus c just once, and you'll see why I just do it once. So we plugged in the upper limit. Now we got to plug in the lower limit, the 1. So everywhere you see an x, plug in a 1. So 1 cubed over 3 plus 3 plus 6. Can you tell me why I don't need to use a plus c when I find a definite integral? None? The c's are going to cancel. That's why you never do it, okay? They're going to cancel anyway, so why bother? So you don't have to do the plus c first. Now we don't have to take out the calculators, not yet. We'll just combine like terms. We got 64/3 minus a 1/3. So how many thirds do we have? So we've got 63/3. Now we've got a 12 minus a 3 plus 9. So what does 63/3 equal to? So 21 plus 9. So we get an answer of 30. Now, nice, we get an integer, right? But what's really nice, when you think about what this answer means, we started out, we said that we're finding the definite integral of x squared plus 3 from 1 to 4. If I were to graph y equals x squared plus 3, what does that look like? Y equals x squared plus 3? Yeah, very good. A parabola. Just moved up 3, right? We found the definite integral from x equals 1 to x equals 4. Oops. Woo! You have to do that. Come back. When we did that and we got an answer, because this is a positive function, that 30 is the exact area, not an approximation. We just found the exact area between this parabola and the x-axis from 1 to 4. Whoa, right? Why didn't we do this before? Well, the whole idea is you use rectangles first, and then you have to think about, well, to get an exact area, we're kind of building up to it. What you're doing is you're taking the limit as the number of rectangles approaches infinity. But that limit turns out just to be the definite integral. Yeah, we've increased the number of rectangles to infinity, and that gave us the exact area. Okay. Wow, we're loving this. Loving this, plus we're getting numbers. It's all good. Let's do another one. Oops, not this one. Okay, so you guys tell me this time. You want to evaluate a definite integral. What's the first thing you got to find? The antiderivative. Now, be careful when you choose the antiderivative of cosine. Is it sine or negative sine? Oh, you guys are so good. So it's sine of x. And I want to put a line here, evaluated from 0 to pi over 2. Okay. You don't have to do the parentheses. I just do that in case there's more than one term. Now you got to know which limit of integration do you plug in first? The top one, right? So you can plug in the pi over 2. So it's going to be the sine of pi over 2. And you plug those into the antiderivative. Now again, we don't need our calculator. We've got the unit circle. So if we think about our unit circle, pi over 2 is up here. The sine of an angle, is that the x or the y coordinate? The y, right? So what's the sine of pi over 2? 1. And then minus the sine of 0, what's the sine of 0? 0, right? So the definite integral of cosine from 0 to pi over 2 equals 1. Now, if you think about what that means graphically, you know, if you think about the cosine graph, it starts up here at 1, and then it goes down to 0 by the time it hits pi over 2. We're saying that the area of this region here equals 1. That's some weird irrational number. It equals 1. Well, isn't that lovely? Riley, is it lovely? Riley, can you believe it? It's not some weird irrational number. Cosine of x from 0 to pi over 2. This area equals 1. What? That's funny enough. I know. He's in shock right now. Can't handle it. All right. Let's try another one. Ready? Yeah, you might have to write yours better than the way I wrote it on your paper. It's not so hot. Write it like that. I know. Sorry. Sorry. Get the antiderivative. What are we talking here? What do we get to finally use today? Yes. Say it. Use substitution. No, we didn't finish it. It's never going away, use sub. Yep. So get the antiderivative. So long. Wait, are you saying it's been so long because it was like 3 days ago? Wow. You're very young, very short life, right? 3 days, that's a huge percentage of your life. Wow, very long time ago. Huh. Yeah, it did. Brian, what'd you make for you? That's what I would do too. So what was your deal? Oh, you went the wrong way. What? Wait, it's 4x to the what? Oh. Phew. Okay. Don't go the wrong way. Alright, so then you gotta think, what do I need inside? A 4, so what do I put on the outside? Now, when you go to rewrite it, everything has to be in terms of u. So realize, these limits of integration, that's from x equals 0 to x equals 2. So don't write those yet. And let's just rewrite everything in terms of u. We'll save the limits of integration. So we have 1/4 the antiderivative of du over what? Really? Du over radical u. The u's just the x to the 4th plus 1. Now, here we have two choices at this point. When you're using u sub with a definite integral, you could just forget about the limits of integration until you actually find the antiderivative and switch it back to x's. That's fine. But you could also just change those too, convert them over. And I want to try doing that with you. So the lower limit was x equals 0. If x equals 0, what does u equal? 1, right? Because it'd be 0 squared plus 1. So that would be a 1. That's how we get the lower limit. The upper limit of integration was x equals 2. But I have to know what it is in terms of u. So what if I put a 2 in here? What would I get? Let me just write that up here. 2 to the 4th plus 1. Anyone know what 2 to the 4th plus 1 is? 17. That's how I'm getting that. If you convert the limits of integration to u also, you can just get the antiderivative, plug in the upper limit, lower limit, subtract, you'll be done. You never have to switch it back to x's. Kind of fun. All right, let's get the antiderivative. Before I can apply the power rule, what do I need to do? U to the what? Negative 1/2. You got to rewrite it with a negative exponent. Now, let me leave that 1/4 there. What's the antiderivative of u to the negative 1/2 du? 2. Oh, I threw him by doing that first. Shouldn't have done that first. First, I should get the new exponent. What's the new exponent going to be? Positive 1/2. So what number do I need to multiply by? 2. That's where that's coming from, because you have to add 1 first. Now, I don't do a plus c. I just put the line here, and I can just go from 1 to 17. I'm going to have to switch this back to x's because I converted the limits of integration. 2/4. 2/4. What's that? So I have 1/2 rad u. And I need to evaluate this from 1 to 17. Now you can just leave the half out, or you could have it in each term. I think I'll leave it out. So 1/2, we plug in the upper limit. We have rad 17. We plug in the lower limit. Rad 1, or just 1. That's our answer. All right, so that time it wasn't an integer. They can't always be integers. Sorry. Well, it's not so bad, though. So with u substitution, if you're using u substitution to get the antiderivative, you can either forget about the limits of integration until after you've taken the antiderivative and you switched it back to x's. Then you can use your original ones. Or you can just convert over the limits of integration, and then you never have to switch it back to x's. Just use the new ones, the u ones. Okay, let's try another one. Ooh, do we need u sub this time? No, we have a formula for antiderivative of either 2x dx equals 2. Who thinks we need a little u sub here? Put your hand up. Right. All right. So yeah, we have an integration formula for e to the x, but e to the anything else is an e to the u. Sorry, if it's not x, it's a u. So what does u equal? So what's the du? Deuce dx. What goes inside? The 2 on the outside. Yeah. Okay. We're going to convert it over. Now, what do you think, guys? Do you want to convert the limits of integration also, so we don't have to switch it back to x's? All right. It's easy enough. Yeah, sure. First of all, tell me the integrand. What are we integrating in terms of u and du? I want to rewrite it in terms of u and du. Here. Right. Yep. Yeah. Okay. Now, we're going to convert the limits of integration over too. That way we'll never have to switch it back to x's. So the lower limit of integration was x equals 0. U equals 2x. So what's the lower limit of integration in terms of u? 0, because 2 times 0, that's how we're getting that. The upper limit of integration was x equals 2. So what is it in terms of u? 4, right? It's going to be 4. That's 2 times 2. That's your 4. Okay? So now we just got to get the antiderivative, plug in the 4, plug in the 0, subtract, right? So we have 1/2, what's the antiderivative of e to the u? Du, e to the u. And we're just going to put the line here, evaluated from 0 to 4. Do you want to leave the half out? We'll just plug in, yeah, I think it's easier. Or else you just factor it out at the end anyway. So which one do we plug in first, the 0 or the 4? The 4. So e to the 4th minus e to the 0. Ooh, what's e to the 0? 1. So we get 1/2 e to the 4th minus 1. Cool. Perfect. Now the next one's really cool, and then I'll just show you how to do stuff on the calculator. All right, this one we don't need u sub. What's the antiderivative of 1 over x dx, or dx over x? ln of the absolute value of x from 1 to e. So we have, which one do we plug in first? The e. So the absolute value of e is e, right? Because the e is already positive, so I don't have to write the absolute value of it. It's already positive. So it'll be the ln of e minus the ln of the absolute value of 1, which is just 1. Who remembers what the natural log of e equals? 1. What about the natural log of 1? 0. Look at this answer. 1. Now again, let's think in terms of area. Oops. Oh, no. I went too far ahead. Okay. The graph of y equals 1 over x, that's an inverse variation curve. What this is telling us is if you took the area underneath this graph from x equals 1 to e, that would be exactly equal to 1. Yep. As long as your function is positive, meaning it's above the x-axis, when you find the value of a definite integral, you've got the area in there, exact. Now, you're probably saying, yeah, but what if it's not always positive? Okay. Like, let's think about the sine of x from 0 to 2 pi. You see how it's like a positive up to pi, but then it's negative. Let's get this guy. What's the antiderivative of sine x? Negative cosine x. Okay, so we're going to plug in the upper limit. Negative cosine of 2 pi minus the negative cosine of 0. Let's think unit circle. Oh, isn't it nice that 2 pi and 0 are in the same place? 0, 2 pi both terminate over there. First of all, what's the cosine of 2 pi? 1. So negative cosine of 2 pi, negative 1. Then we have minus a negative, so plus the cosine of 0. So what do we get for the value of the definite integral from 0 to 2 pi? 0. We get an answer of 0. Now, when their function was positive, it gave us the total area between the graph and the x-axis. Why do you think we're getting 0 this time? What do you think it's given us when the graph is sometimes positive and sometimes negative? The difference. That's exactly what it's giving you. It's giving you this area above the x-axis minus the area below. So if they're the same, you'll get 0. If you have more area underneath, you can get a negative answer. You can get a negative answer. So that was very smart. Now, every one of these problems that we did could have been done by your calculator. It's a nice thing to know, but it's not a substitute for knowing how to do it using the fundamental theorem of calculus. But I do want to show you both ways. So if you have your calculator, we're going to do the first example. I'm going to show you 2 ways, and it's listed on the top of your practice page how to do it. Oh, where's my calculator? No paper. The first way we're going to find the definite integral is using the math menu. So we're going to go to Math 9. When I get there. Okay. Out of here. Okay, if you press Math, Choice 9, fnInt. Now, what it wants from you is, first of all, the function. And in the first problem, we did x squared plus 3. So I'll enter x squared plus 3. Then you got to enter comma x. Always you have to put in the function comma x. You're telling the calculator treat x as a variable, not as whatever number stored there. Now remember we want to integrate from 1 to 4? When we do it by hand, we plug in the 4 first and then the 1. On the calculator, it's lower than upper, not upper, lower. So on the calculator, you put in comma 1, comma 4. When you press enter, you get 30, which is what we got for that first example. Now there's a cooler way that I want to show you to do it, using the CALC menu. Let me show you this other way. Did everyone get that? Okay, the other way, you have to first put the function in, you have to, in y1. So go to y1 and put in your x squared plus 3. Yeah, it was x squared plus 3. X squared plus 3. Now we want to graph it. I have to fix the window. If I go to zoom 4, it's not high enough. See, it's too, so I just want to change the y max to 20. So if you start with zoom 4, just go to window and change the y max to 20 so you can see it and graph it. Get ready for cool. You ready for cool? Okay, we're going to use the CALC menu with the graph. So the CALC menu is over the trace. So we're going to press second, trace, option 7. It's asking for the lower limit. So just type in 1, enter. Upper limit, what are we going to type in? 4. And watch what happens when you hit enter. Bam!
Wow.
Isn't that cool? Now the way you do both is up there at the top. I have them both listed. Usually you don't do this, even though it's really neat, because this you have to graph it first. Usually you use the math 9, put in the function, comma, x, lower, upper. When you're doing the homework tonight, if you want to do some of them with the calculator, that's fine. But don't do all of them with the calculator. You really need to practice using the fundamental theorem of calculus. Get the antiderivative, plug on the upper or the lower, and subtract. Okay? But it's fine if you want to try some with the calculator or just check with the calculator. It's okay if you want to do some, but not all. Got it? All right.